Welcome back to AllAboutRx. In this comprehensive pharmaceutics lecture, we dive into the science and technology of micromeritics. We're going to be exploring exactly how particle size, shape, and surface area critically influence the physical, chemical, and pharmacological properties of pharmaceutical dosage forms. Basically, today is all about understanding how these tiny microscopic particle properties dictate exactly how a drug behaves once it's inside your body.
Here is our roadmap for today's explainer. We'll start with an introduction to micromeritics, cover the golden rule, look at particle shapes and diameters, and then sieve analysis classification. After that, we'll analyze polydispersed powder systems before finally wrapping up with pharmaceutical applications.
Section 1, Introduction to Micromeritics.
So what exactly is this field? Well, by definition, micromeritics is the science and technology of small particles. The foundational unit of measurement here is the micrometer, also known as the micron. You will learn that working on this incredibly small scale allows us to accurately determine a particle's size, its shape, and its surface area. It's really the core language pharmacists use to figure out how a powder is going to physically behave in the real world.
Let's move right along to Section 2, the golden rule.
This is absolutely crucial to understand. The golden rule of micromeritics states that decreasing a particle's size exponentially increases its available surface area. And this physical change, it triggers a direct cascade effect. More surface area leads to much faster dissolution in the body's fluids, which ultimately leads to faster pharmacological action. It's a pretty simple chain reaction, but it is literally the backbone of effective drug design.
To put that into perspective, this golden rule brilliantly illustrates why certain drugs are formulated the way they are. Take griseofulvin, for example. Normally, it has very low oral solubility, but by reducing its particle size during manufacturing, it rapidly breaks down in the gastrointestinal tract and easily passes through membrane pores, getting absorbed so much faster. We see the exact same benefit with drugs like tetracycline and aspirin. Shrinking the particle size significantly enhances their rate of absorption. It's a real game changer.
Section 3, Particle Shapes and Diameters.
Now you might be thinking all particles are just tiny little spheres, right? Well, not exactly. The lecture covers the important distinctions here. On one hand, we have symmetrical particles, which are often perfectly spherical. Because they have a specific crystal shape, it's incredibly easy to calculate their volume and surface area using just a simple mathematical diameter. But on the other hand, we have asymmetrical particles. These are irregular and lack any specific crystal shape. As that asymmetry increases, figuring out their exact surface area and volume becomes a highly complex mathematical headache.
To solve this asymmetry problem, scientists developed a brilliant workaround. We use what are called equivalent diameters, specifically surface, volume, projected, and Stokes diameter. Essentially, what these metrics do is allow us to mathematically treat an irregular, weirdly shaped particle as if it were a perfect sphere. For instance, the volume diameter simply assumes a theoretical sphere that has the exact same volume as our asymmetrical particle. It takes the chaos of irregular shapes and standardizes it.
That brings us to Section 4, sieve analysis classification.
Okay, so once we can measure these individual particles, we need a way to classify millions of them at once. To do this, powders are sorted based on their ability to pass through standard sieves. This gives us clear sieve range classifications. We have coarse powders, which are large particles that can't pass through a number 20 sieve, intermediate powders sitting between sieve 20 and 200, and fine powders, which are small enough to slip right through a sieve smaller than number 200.
Section 5, Polydispersed Powder Systems. Here is a major curveball. In the real world, almost no powder is perfectly uniform. Most mixtures are what we analyze as polydispersed powder systems. This simply means that a single sample is a collection of particles featuring multiple different sizes. Because of this, you will find that understanding the complete size range and distribution spread is absolutely essential. You cannot just rely on a single average particle size. Two completely different powders could mathematically share the same average diameter but behave totally differently in a patient's body or inside a manufacturing machine. You really need the whole picture. And we can actually visualize that whole picture using frequency distribution curves. By plotting the particle size range on the x-axis against the frequency on the y-axis, we produce this skewed, bell-shaped curve. It visually reveals the peak mode of our sample, showing us exactly where the vast majority of our particles sit within the total size spread. It's incredibly satisfying to look at. Finally, let's jump into Section 6, Pharmaceutical Applications. So why does all this actually matter? Well, you'll discover how micromeritics directly impacts almost every single facet of drug design. It optimizes drug release and dissolution by ensuring particles have the precise surface area needed for intimate contact with bodily fluids. It enhances the physical stability of suspensions and emulsions simply because smaller particles stay suspended much better. And critically, it guarantees dose uniformity and ideal powder flow properties during tablet and capsule manufacturing. If your powders don't flow predictably into the molds, your pill dosages are going to be completely inconsistent.
So, if particle size alone dictates whether a life-saving drug actually dissolves in time to work, what other microscopic forces do you think are secretly controlling the medicines in your cabinet? Thank you for tuning into this lecture. If you found this breakdown helpful, please make sure to like, subscribe, and drop a comment below with any questions or topics you want covered next. See you in the next Explain.